I'm back with my next lesson. So today we have our new chapter. So it's chapter 11 and it's the first section. So this section is about limits. So limits of trig functions. So how do we do that? So limits of trig functions. Okay, first try recalling. When we first started learning about limits, we started off with a graphic way to evaluate that. So basically the idea is, let's say pretend there's a graph like this, something like this. Pretend this value is 3 and 1, 2, 3, 4, 5. Okay. So let's say if I ask you limit of this function, I know it's going to be a quadratic function. So when x approaches to 3, so I'm asking you to estimate the value of this function when x is getting closer and closer to 3. So it means on the graph, once your x value is getting closer and closer to 3, what's the estimated y value correspond to that number? So if I look at my graph, well, what I see is it's 5. So that's what limit is. Basically, the easiest way to say is it's just finding estimated value of y or expected y value. That's what a limit is. That's just the shortcut or the easiest way to say that. Okay. So once it comes to trig function, just like normal function, so I'm going to start off with direct substitution. So we have direct substitution. So let's talk about those rules. I'm just going to show you first 3 because reciprocal would be the same thing as well. So let's say I have limit of x approaches to, just pretend it's c, and it's sine of x angle. So basically direct substitution is telling you to substitute that x value with the x approaches to number. So x approaches to c, so I'm just going to do direct substitution and this becomes sine of c, and later on you can just evaluate that function. So same thing applies for, let me show you one more. Cosine x approaches to c, so this is going to be cosine c, and limit of tangent x when x approaches to c, so this is going to be equal to tangent of c. So same thing works for reciprocal functions, which are like secant, cotangent, and cosecant functions. Okay. Along with these rules, I still have 2 more equations to talk about. So there's another equation, or I would say it's one of the properties which always work, right? So let's say I have limit of angle x, this divided by just x, and x approaches to 0. This equation, if you see something like this equation always going to be equal to 1. This would also work if you have it to reciprocal. So let's say you have limit x approaches to 0 and it's x over sine x. It would still be equal to 1. Actually, in order to justify this whole equation, there's a long theorem you can actually look at online, or you can look at it in your textbook, but I'm just going to show you something really quick just to give you kind of idea about this equation. So pretend, let's say, okay, when I say x is approaching to 0, means that x value is so close to 0. So let me show you few, I'll substitute numbers, let's see what happens. Okay, if I say x approaches to 0, let's say it's 0.1. So limit, let's do direct substitution, plug 0.1, divide by 0.1, and let's see if it's equal to 1 or not. Okay, you can type it in your calculator. Don't forget to set up your calculator to radian mode, all right? Because the angle I'm talking about, it's in radian right now. So that's what I'm talking about. So if you put it in, so I already have these numbers ready. So if I plug it in, it's going to be, here you go. Let me show you one more. Let's say I have limit x approaches to 0. This time I have 0.01 divided by 0.01. Let's see what happens. It's 0.9998, which is still kind of closer to 1. So it means this equation also works. Even if you take it to reciprocal, that would still work. All right. So you can even try that if you want it. That's my first equation. So let me circle that. So this or this is the same thing. So second equation I have is, it's limit x approaches to 0. I have 1 minus cosine x over x. If you see a pattern like this is always going to be equal to 0. And I'm sorry, no reciprocals. For this equation, reciprocal doesn't work. So try not to do that, okay? Again, just to justify this equation, I'm going to show you, I'm going to plug in numbers so that you can actually see that happening in here. So let's say if I plug in 0.01, if I have 1 minus cosine, I would plug in 0.01, divide by 0.01, and if I do that, my answer is this. Let's try one more number. Again, the reason I plug in 0.01, because when I say x approaches to 0, I'm talking about a number that's getting closer and closer to 0. I don't know if that makes sense. That's the reason I'm plugging those small numbers there. So let's say my other number is 0.001. Divide by, oops. So my answer is going to be, there you go, which is kind of true. Yeah, it is getting closer and closer to 0. So that is my second equation. All right. Now let me show you a few examples. How do we actually find or evaluate limit of any trig function? So here comes the first one. I see sine x, limit x approaches to 0. Okay, this is not one of those two equations, so I can't apply the pattern. So I would just do direct substitution right away. So I would plug in 0 for sine, for the x value. I would substitute x with the number it's approaching to. Now you just have to evaluate. And when I say evaluate, basically, you could either use your calculator, you can look at your flashcard, whichever way. So sine of 0 degrees, it's going to be equal to 0. Here you go. All right, so let's say I have limit x approaches to 0, and it's tangent x over sine x. Okay, for this part, tangent, let's try simplifying this function first. So tangent can be written as sine x over cosine x, which is dividing by sine x. Okay, now let's simplify. So sine over cosine divided by sine, or I would say multiply by the reciprocal. Or I'll just write it down here. Sine x over cosine x times it by the reciprocal of the bottom expression. Simplify if possible. I simplify, ended up getting 1 over cosine. Once you're done simplifying the function, then we evaluate the limit. Okay, now let's apply the limit. So limit x approaches to 0. If I plug in 0 for x, because this is now one of the patterns, so the cosine of 0 degrees is equal to 1. So I would do 1 over 1, which is equal to 1. Here you go. Let me show you one more. Actually, I have a few more. So I have tangent x over x and limit x approaches to 0. All right. Okay, tangent can be, again, always try simplifying first. So tangent can be written as, and divided by x or the reciprocal. Here you go. Now, what I see is, I know sine x over x is equal to 1, right? But this is not the way it should look like. I could actually rewriting this so that I can apply the pattern. So let's try rewriting. So let's play with this equation. How about if I write this equation like this? Isn't it still going to be the same thing? Now, the reason I would rewrite this part here, because I know once I see something like this, I could apply that first pattern. Sine of x over x is equal to 1. So let's plug it in. So you already know this part is equal to 1. So it's 1 over cosine, which is not one of the patterns. So then I would just apply the limit. So this is limit x approaches to 0. 1 would stay the same. So plug in 0 for substitute x with 0. This is 0. So 1 is already there. So 1 divided by 1. So it's still going to be 1. So basically, whatever the example I just showed you, that's one of, like, I can drive another pattern from this equation. So anytime you see tangent x over x, that's also going to be equal to 1. So I would say that's your third property you could use. Next time you see something like that, like, I would just rewrite that. So if you see tangent x over x, and limit x approaches to 0, this is also equal to 1, same as sine function. Okay, let me show you a few more. I know this lesson is going to be a little longer, but I guess you really need to look at those examples in order to understand your homework assignment. All right. Okay, so I have one more. So I see limit of sine of 2x over x, x approaches to 0. Okay, again, I know sine of some angle divided by the same value equals to 1, right? But what I see is, for this problem, the angle is 2x. So the bottom number should match up with that. But it doesn't, right? So now you can, just like that pattern recognition, so you can actually bring in something. You can either bring in, this time you can bring in a constant or a variable is the same thing. It's not a problem, okay? So what I see is this bottom number has to be 2x. Instead, I just see x. So what I would do is I would bring in the number. So let's just bring in, again, just like pattern recognition. You have to put 1, means that number divided by that number. So I know the bottom number would complete the pattern. So I would factor out the top one. So now this new equation, after that new number, would look something like this. I hope this makes sense. Now let's apply the property. So I know sine of some angle divided by the same number, it's equal to 1. So my answer would be 2. There you go. I have 2 more examples. I'm sorry, guys. Yeah. So let's say I have this one here. So I have 7 times 1 minus cosine x. Oh, my bad, 3x over x. Okay, for something like this, what I would do is, I know my second equation, which is 1 minus cosine of some angle divided by the same number, it's equal to 0. So this pattern almost looked the same, but the bottom number is not same as the angle. So there's a 3 that's missing. So again, just like always, just like the last example, I would say, I would bring in a 3 over 3. So this bottom 3 would complete the pattern. So let's rewrite it. So I already have 7. I would bring in other 3. I already have 1 minus cosine of 3x. The bottom number would be 3x. Now let's apply the limit. So you know 3 times 7 makes 21. If I apply the limit to this number, so this is going to be equal to 0. So 21 times it by 0, this answer going to be 0 at the end. Here you go. The last example, get ready. All right. And I hope you'll see a pattern in there. Okay, next one. I see sine of 5x over sine of 7x. Okay, and the limit, x approaches to 0. Okay, normally for the equation, you have to have sine with some angle on the top and divided by just the number itself. Just the number, right? Not other trig function. So let's try rewriting this first. So let me say if it's something like, let's rewrite it like this. Why? Because I know even the reciprocal for this property would work as well, right? So I just wrote it into 2 different things, because for the first one, I would just apply the first one. And for the second part, I can use my reciprocal for the same property, right? Okay, now let's plug everything in. For completing this part here, I have to have 5x in there. There's a 5x missing in here. So let's just say, or I can just, let me just rewrite it. How about if I leave some space in there? That way it would be easier to actually adjust those numbers later on. So let's use this now, color. So for this part, I have to bring in 5x over 5x. And for this one, I have to bring in 7x over 7x. Okay, almost there. So for this first part, this bottom number would complete the pattern. For this one, second one, the top one would complete the pattern. So let's rewrite it. So I see sine of 5x over 5x. Second one, I would say 7x over sine 7x, and this one here. And now I can simplify the x's here, okay? So this and this equation is going to be equal to 1 once I apply the limit. Once you apply the limit, So this is going to be 1, and then I see 5. Then this is also going to be 1, and that's going to be 1 over 7. And if you put it together, answer is 5, 7. So here you go. Now basically, if you look at this equation, there's a pattern. Basically, your answer always going to be the coefficient of that angle. So you can just set up a fraction like what I see, 5 over 7. Let me take you back to this one here. So isn't it, this is 2x divided by x, which is simplified to, oh, my bad, which is simplified to 2. That's what I had at the end. So I know I already told you the shortcut, but that doesn't mean you're actually going to use that shortcut to solve all the problems. So make sure you show me enough work for every single problem. So yeah, this is pretty much all. So enjoy your homework assignment. All right, stay safe. Bye-bye.